guys, so now we're going to start looking at absolute maxima and minima. Um, I think I've discussed this a fair bit in class before, but when you have a function has two types of maximums. Like if you have a function that looks like that curve and it ends here and here, if I said what's a local maximum, that there is called a local maximum because it goes up to a point, which is a maximum, then comes back down. So we call that a local max. This point here is a local min. And then we also have this point here, which is an absolute max. Absolute min. Absolute min. And then we have this point here, which is an absolute max. Now, a local max can also be an absolute max because if this function was only defined up until here, well then the local max would also be the absolute max. But an endpoint where the maximum occurs isn't a local max. This is always just called an absolute max. Whereas this is an absolute min, but this is a local min. So local mins only occur at turning points, or local maxes occur at turning points. Now, to show you how this makes sense in terms of the calculator, let's have a look at this function, x squared plus 2, and it's between negative 2 and 4. So if we go to, I just forgot the function already. It is x squared plus 2. Okay, so plus 2 given. Negative 2 is less than or equal to x, which is less than or equal to 4. Okay, so there's our curve. I'm just going to go zoom initialize. Move it down. Zoom out. Okay, so there's our full function. Now, if we do gsolve and then min, it tells us our turning point is at 0, 2. If we go analysis gsolve max, it says that there is none because we don't have a local maximum, because max and min means local max, local min. So we know we've got a local min at 0, 2. And we can also check analysis gsolve fmin. That returns the lowest value on the domain. So our local max doesn't occur. Our local min is 0, 2. And our absolute min is the same because it's the smallest value on the domain. So our absolute min is 0, 2. And our absolute max, we use fmax, and it tells us it's 418. So absolute max is 418. So if it says what is the absolute maximum, abs max is our y value, that's 18, and our abs min is also the same as our local min, which is 2. Okay, so that's the difference between an absolute max, absolute min, local max, local min. Now, I shouldn't have rubbed that out, but here I've got another function. So I have got x cubed plus 2. It's between negative 2 and 1. So, because this function is always increasing, the absolute max and min are going to occur at the endpoints. Okay, so there's no way that you're going to get an absolute minimum or max that doesn't occur at an endpoint. So we can chuck in an endpoint. If I put it into here, I get f of negative 2 is equal to negative 2 cubed plus 2, negative 8 plus 2, which is negative 6. So that's our abs min, negative 6, because it's our y value. And our max is f of my right-hand point, which is 1 cubed plus 2, which is 3. So my abs max is equal to 3. Sometimes you get a function, you need to find what the highest value is on the domain, and it won't necessarily occur at a turning point. It might occur at an endpoint. So you need to check and see if it occurs at either the endpoint or at a maximum or minimum value. So when the turning point occurs, and also at the endpoints. Okay, here. So from a square piece of metal, side length 2 meters, 4 squares are removed as shown. The metal is folded about the dotted lines to give an open box. Sides x centimeters. Height with sides of height x centimeters. So that's x. That's x. They're all x's. So this length here is that whole length, which is 2 minus x there and x there. So 2 minus 2x. And it's a square. So that's also 2 minus 2x. And we know the height, if we were to fold these sides up, like fold them up, we'd end up with a box. And that height is x. Okay. Show that the volume can be given by that. So we know the volume is length times width times height, which we just worked out was x times 2 minus 2x times 2 minus 2x, which is x times 4 minus 8x, and then plus 4x squared, which is 4x cubed minus 8x squared plus 4x. So that's as required. Okay, sketch the graph of V against x for a suitable domain. Now, to work out our suitable domain, first we know x has to be greater than 0, otherwise we wouldn't have a three-dimensional box, like we wouldn't have a box that's going up. And we also know that the side lengths must be greater than 0. So 2 minus 2x has to be greater than 0. Negative 2x has to be greater than negative 2. X has to be less than, when I divide that across, 1. So our suitable domain is 0 is less than x, which is less than 1. If we sketch that function, we can go back to our factorized form up here. So if I take a 2 out and I take a 2 out, I'm going to have a 4 at the front because I take a 2 out of that bracket and a 2 out of that bracket. I'm going to have 1 minus x squared. So if we go to sketch it, we know it goes through 0 and it goes through 1. We know this is a turning point, the x squared. I forgot there's another x. So we get 4x, 1 minus x squared. Okay, so it's an x cubed, so it's going to go up at the end. And 1 is a turning point, so it's going to turn around and go like that. Now, our maximum is going to occur somewhere between 0 and 1, obviously. The suitable domain, we wanted to restrict it, so between these 2 points. Okay, we shouldn't really, when you're drawing this, you shouldn't really have the endpoints defined. So when that goes up like that, because if x equals 0 or if x equals 1, then it's not going to be a three-dimensional shape. Like it won't hold that form. So 0, 1. Okay, if the height of the box must be less than 3 meters, i.e. x is less than 3 meters, what's the maximum volume of the box? So we know, let's find the turning point. So dv dx is equal to 12x squared minus 16x plus 4. If we set it equal to 0, take out 4 as a common factor and divide it to the other side, 3x minus 4x plus 1. Okay, so we can have 3x minus 1, x minus 1. So we know we've got a turning point at x equals 1/3 or at 1. Now, if there's a turning point at 1/3, 1/3 is the same as 0.33. So if our turning point is at 0.33, let's say that's our turning point at 0.33, but we know our maximum value is 0.3. So if we look here, 0.3 is going to occur to the left. So if we get rid of this part of the graph and say, okay, when's our maximum value going to occur? It's going to actually, it's going to occur at 0.3 because this function's increasing. The maximum occurs at 0.3. So we want to find our maximum volume. I'm just going to scrap this so I've got some room. We know x equals 3 on 10. So our maximum is v equals 4 times 3 squared is 27 on 1,000 minus 8 times 9 on 100 when I square 3 on 10 plus 4 times 3 on 10. Okay, let's see what we can do. I'm just going to put it over 1,000. It's going to make it easier. 4 times 27 is 108 on 1,000. 8 nines is 72, but that's 72 on... That's 72 on, sorry, I was looking ahead. 72 on 100, which is 720 on 1,000. And I've got 4 times 3 on 10, which is 12 on 10, which is 1,200 on 1,000. Okay, so we get 1,308 on 1,000 minus 720 on 1,000. So that's going to be 280 plus 300, 588 on 1,000. And then that is going to be meters cubed. So that's our maximum volume if we have a restriction that makes the point 0.3 an absolute maximum. And you can check it on your cards, 4x cubed minus 8x squared plus 4x. Or we could just do 4x 1 minus x squared. So there's our graph, and you can see zoom initialize. We only want it between 0 and 1. So given 0 is less than, not less than or equal to, 0 is less than x, which is less than 1. Sketch it. Zoom auto. That's not very nice, is it? Let's go from 0 to 1, and then go from 0 to, let's go 5. So there's our graph. Analysis, G-solve, max. Okay, so our max is 0.33, and then whatever that value is. 6.59, 5.5926. But if we restrict the graph to go up until 0.3, sketch it. Now if I go analysis G-solve max, there is no max. However, there is an absolute max, which is 0.3 and 0.588. Okay, so 0.588, which is exactly what we got here. Okay, so that's absolute maximums and minimums. So if they ever ask you for a maximum or a minimum on a domain, you've got to check and make sure that it could be a turning point, but it also could be an endpoint.